Okay, we're ready to start. Welcome everyone to the OpenACC course. Thanks a lot for joining us today. It is early morning here in California, and we're ready to start the day with OpenACC. So my name is Julia Levitas. I'm a product manager at our Tesla group, and will help with the office hour today. So let me start with some housekeeping items. First of all, every session of the course will be recording and available for you to review on our OpenACC course page. I just posted the link to the recording in the chat window. So it's OpenACC course page, developer.nvidia.com/OpenACC course. Please check it out later during the day, and we will post the recordings there. All the lines are muted, so please submit your questions through a chat pod on the left-hand side towards the bottom of the screen. We'll answer as many questions as we can today and publish Q&A together with the recording on the course page. Again, the course page is in the chat window for your reference. With that said, I think we're ready to start. Justin Luchins is our instructor today and here to answer your questions. Justin, it is all yours.
All right, thank you. I'd just like to start out by introducing myself. So I am Justin Luchins, as Julia said. I am a DevTech at NVIDIA. DevTech is sort of a unique role that NVIDIA has. The role of NVIDIA of DevTech is to go into applications, understand them in terms of their performance, understand them in terms of customers, what their needs are, and take the information that we gain from understanding the application and feed that back into our design process. So part of this means that we go through and we optimize applications. Part of it means that we go and identify limiters. Another part is that those limiters then go into our design process to feed the next generation of hardware. So I've been doing this role for about 5 years now. And in this process, I have become, I would call it, an expert at CUDA, and I've also become an expert at OpenACC. I was involved in OpenACC before OpenACC was announced, helping design the language and helping design the roadmap for it. So today I'm going to go ahead and answer a number of questions for you, and we have a number of them that were given out. But before we do that, let's go ahead and just review the schedule. So you've already had the introduction to OpenACC on October 1st. Today is October 6th, and we have the office hours. So this is going to be a 1-hour session where you are free to ask questions in the chat window, and we will go ahead and answer as many of them as we can. All right, so on October 15th will be our next meeting, where will be another presentation on profiling and parallelizing with the OpenACC Toolkit. So please make sure to put that on your calendar. All right, so a number of questions were submitted during the last presentation. We've gone through most of them, and we have answered them, and we have published a document. You can find this document here at https://developer.nvidia.com/openacc/course. So please go download that document and review it after this talk today. Now what we are going to do is go over some of the main questions that we were asked. These are some of them are in the document, some of them are not. Most of the questions that were answered in the document will not be covered today, so it's very important to go back and review that document. So question 1 is, what is the basic difference between CUDA and OpenACC, and OpenMP? This is a very good question. So CUDA is a very low-level language. It's very similar to C, C++. It actually is C and C++ with a few extensions. It is low level in that you get to express exactly what your computation is doing and how it is doing it. You express the parallelism explicitly, and there is no sort of compiler deducing what parallelism to expose. OpenACC, on the other hand, is a higher level than CUDA. It is a pragma-based parallelization scheme where you are going to give hints to the compiler on how to parallelize your code, but not necessarily tell it the exact steps it needs to take to do it. The compiler is then going to do some analysis and determine what it thinks is the best way to parallelize your code based on the information that you have given it. These two methods, CUDA and OpenACC, both achieve the same goal. That is, they parallelize your code to run on a CUDA-enabled hardware. OpenACC also parallelizes the code to run on other hardware and not just CUDA. One thing to note is that CUDA is typically going to give you more control. You are explicitly controlling the exact form of parallelism that you're going to expose, and therefore you get to tell the hardware exactly what to do. OpenACC is higher level, so the compiler makes those decisions. What this means is that typically a well-programmed CUDA code is going to perform faster than a well-programmed OpenACC code. However, in many cases, they should be similar. OpenMP, on the other hand, is an alternative to OpenACC, which focuses on parallelizing on the CPU primarily, with recent extensions to parallelize on accelerators. It is a slightly different scheme. However, it achieves a lot of the same goals. If you are familiar with OpenMP or OpenACC, you'll notice that they are very similar. However, there are some minor differences. Now, there is a lot of work going into both the OpenACC and OpenMP committees to try to get these two to standardize and agree on a set of features. Currently, the features are overlap significantly, but there are a few key distinctions between them. In general, what I find is that OpenMP is much better at doing sort of CPU code and running on the CPU. That's what it is designed for. But the maturity for going towards accelerators is not as good yet. OpenACC, on the other hand, has a few more years of maturity for targeting accelerators, and therefore its accelerator compiler is better than the OpenMP's. All right, so let's go on to question 2. What OS is supported by the OpenACC Toolkit and the PGI compiler? So the OpenACC Toolkit or the PGI compiler is supported on Windows, Linux, and Macintosh. However, it's only supported on x86 platforms. So it's not supported on ARM Linux. Number 3, is PGI the only OpenACC compiler available? Absolutely not. There are other compilers that are out there. We just have been using PGI as an example. But examples of other compilers that are out there include Cray. And in the development branch, GNU now has an OpenACC compiler also. Question 4, can libraries be used with OpenACC? The answer to this one is absolutely yes. And I encourage you to use libraries with OpenACC. In general, the very first thing you should always do when optimizing or accelerating your code to run on a CUDA-enabled device is to look and see, is there a library which does does what I need it to do? So if you're using BLAS routines, look at cuBLAS. If you're using FFT, look at cuFFT. Right? These are things that you should always do first because those libraries exist, and there's been a lot of work to go into accelerating those on the GPU. And they're probably the most efficient ones that are out there. Writing your own would likely not achieve the same performance that we have gotten over the years in our own internal libraries. So please use libraries with OpenACC. They do interoperate just fine. Question 5. Does OpenACC support multiple GPUs? Yes is the answer to this. OpenACC does support multiple GPUs. There are API calls that you can use to select which GPU you want, and you can do things like query how many GPUs are available. So this is all supported. It's not covered in our last presentation, and I don't know if it's covered in the future ones, but if it's not, I suggest consulting the documentation to get more details on that. Question 6. Does OpenACC use shared memory in a proper way? So the answer to this is it does use shared memory when it sees that it can do so. So for example, if you are doing a reduction, it will often do parts of the reduction in shared memory. There's also a few directives that you can do to help give hints to put things in shared memory. One example of this is the cache directive. Now, in general, OpenACC may not use shared memory the same way that you would in CUDA. In CUDA, we often use shared memory to communicate between neighboring threads. OpenACC, on the other hand, its parallelism model is really describing parallelism from the point of view of a single thread, and it's not describing it in terms of collaborative work between different threads. And in this case, OpenACC is not going to likely use shared memory. Q7. So what is the difference between Matlab with Parallel Toolbox and OpenACC? Matlab with Parallel Toolbox is just another way to achieve parallelism, but is built into Matlab. So think of this as a parallel solution to OpenACC. It is built upon CUDA under the hood. It uses many of our libraries where possible, and it works just side by side with OpenACC. Question 8. How many dimensions does OpenACC support in calculating vectors? This is an interesting question, and by what I think they mean here is can you put vector on multiple loops in order to get multiple dimensions of vectors? The answer to that is no, you cannot. You can only put a vector loop on a vector on a single loop, and the same is true for gang and for worker. You can only put them on one loop. You can put them on different loops, but you have to put them in order: gang, worker, vector. Now, one thing you can do is if you have multiple loops that you want to parallelize over, there is what is called a collapse clause. Collapse will collapse two loops into one. And in that way, you can essentially put vectors over multiple loops. Question 9. Can two applications run in parallel on the GPU that is optimized with OpenACC? This is a good question. So two applications can share a single GPU. However, it is not recommended. In particular on older hardware, there are potentials for bugs that will come in from it. On newer hardware, it will run fine, but it will run slower. In general, if you want to have multiple applications share a single GPU, you would use what we call is MPS, our Multiple Process Service. For this, I suggest that you look on either some of our blogs that describe what MPS is, or look into our documentation on that to see how that works. Question 10. How many kernels can I generate, and is there a limitation? The answer is there's no practical limit on the number of kernels you can generate. In reality, there probably is some limit that's not been counted. Right? You could eventually maybe exceed some buffer in the compiler, but in reality, you can have as many kernels as you want. We're going to quickly jump ahead for a second, do a review, and then I'm going to go over a couple documents for you, and then we're going to go answer questions you've been asking while I've been answering these top questions. So let's go ahead and go to the next slide. So where can you find help? There's a number of places. So we have all of the recordings and Q&A available online. So what I'm talking about right now will be on recording for you to re-listen to. And of course, the previous class will be there too. And the Q&A questions that are asked today and were asked previously will also be included there. In addition, there's a great resource called Stack Overflow, a great place to ask questions, and a lot of people are on those forums. They answer questions, and those questions get archived and saved so that other people coming to ask the same questions can see those results, those same answers. Finally, you can also download the OpenACC Toolkit at the developer.nvidia.com/OpenACC. Additional resources that we have include the Parallel for All blog at devblogs.nvidia.com/parallelforall. This blog is a very useful sort of coffee break blog where we post small articles for people to review. And they're typically things that will take you maybe 5 or 10 minutes to digest. They're very useful because they give you tips from some of the experts in various fields that have been working in CUDA and OpenACC for a long time. We also have our GPU Technology Conference once a year in the spring time frame. This year, I believe it's at the beginning of April. You can go there and register if you would like to attend. In addition, we have all of the talks from the previous 5 years or so that has been going on. All of those talks are archived and available to replay and watch. So those are great resources to go get more information. If you have a topic that you are wondering what's been done, go to the website there and search for your topic, and you may find already there's a number of topics that are there. Finally, there's the OpenACC website. Please go there. The documentation for OpenACC is there, and you can go ahead and get some cheat sheets which show you, little things you could print up next to your desk. That'd be next to your desk that would help you quickly look up references to syntax and formats. All right, with that, I'm going to put it back on the schedule. I'm not going to review it again, but now I'm going to go into the sort of live Q&A part of this discussion. All right, so let me go ahead and start looking for some questions, and then go ahead and answer. So first one is, I'm going to answer is there any criteria to choose the best combination of gangs, workers, and vectors? The answer is there are some things that you should try to do. The first thing is that I would focus on is the number or the size of your vector. So in general, your vector size you would want to be divisible by 32. You could also make it say 16 or 8 and probably be okay if you had enough workers. But in general, your vector size should be divisible by 32. The product of the workers in vectors should probably be at least 128 in size, but you shouldn't go much, you don't want to go too much larger than that. Gangs you should make as large as possible, just to expose as much parallelism as possible. All right, so here are, the next question is, are there free Fortran compilers able to handle with OpenACC? So are there Fortran compilers that are able to do OpenACC that are free? The answer to that is, well, the PGI compiler does have an academic and a development license, which is my understanding is free, not for deployment. If you want to deploy, then you'd have to purchase from PGI a license. The GNU compiler that is out there in the development branch is also free, as all GCC compilers all GNU compilers are. Let me grab another question here. Does OpenACC support STL vector of structures? That's a good question. So you can always, within an STL vector, you can get a raw pointer out of that STL vector and then use that in OpenACC. The vector itself, so you couldn't do, for example, a copy clause on just the vector. You'd have to do it on the raw pointer of the vector, is my understanding. Find another question for you. Does OpenACC use shared or distributed memory? So if I understand this question correctly, it's asking, I look at as a distributed memory as being something like an MPI process, where every process has its own distinct memory system, and then shared would be more like OpenMP, where everybody is sharing the same memory system. OpenACC uses a shared memory system, right? All of the threads can access all of the memory, and that's why it's very important that when you do your clauses, if you have something that you want to be private to each thread, you can use what's called a private clause to say that this memory should be private to that individual thread. And for more information on that, you can consult the documentation, and it may be covered in future weeks also. Right, so there's another question. We answered that one. Does OpenACC support Xeon Phi yet, in particular the PGI compiler? So my understanding is that it does not currently support Xeon Phi, but it is on the roadmap. So while it's not there yet, I suspect it will be there in the near-term future. Finding another question. If we have code that uses CUDA and OpenACC, which compiler should we use? Can we use PGI? So the answer to that is you can use any compiler you want. You can use PGI, you can use CUDA. I mean, you're going to use NVCC for CUDA, but for the OpenACC part, you could use PGI, you could use GNU, you could use Cray. All of those would be options for you. Use whichever one is most appropriate for your application or for your environment. And just a quick point out here that using both of those is completely acceptable. You can interoperate OpenACC and CUDA in the same application without a problem. Right. Let me look and see if I can find another good question. Just have to kind of move the questions I've answered out of this area of the documentation of the document. Okay, so here's a good question. When managing data movement, does the data region need to go outside of the kernel's region? If so, then why? So the answer to this is yes. The data movement sits outside of a kernel's region. A kernel's region really is just saying all of this is an area of code where we want kernels to run, and the compiler is going to deduce what kernels to put in there. But the data should already be present. If it's not present, what will happen is data will get implicitly copied down and copied up on every single kernel call that happens. So the kernels will happen implicitly there. The data region will happen implicitly. So it's better to have an explicit data region on the outside of that. You cannot put a data region inside of a kernel's region. It needs to be on the outside. Right, another good question. So one question was more of a comment somebody had, and I'll reiterate this, that the OpenACC compiler for GCC is in greater than 5.0, and that's, I think, in the development branch, but I may be stale on my knowledge there, and it may actually be just in GCC 5.0 stable. Finding another question. Keep the questions coming. I thank you for your questions. If I'm not clear on one, please re-ask a question or ask for clarification, and I will go back over that. So somebody's asking, I think I understand the question. I think the question is, does the OpenACC toolkit contain the latest Nvidia GPU toolkit? My understanding is yes. At least I think the latest PGI one currently supports 7.0, and when 7.5 is released, if it hasn't, I know it's going to be released soon, but if it's not out yet, they will release an update where it will come with 7.5. Question, does OpenACC support a four-dimensional array such as AIJKL? And the answer is yes. It'll support any size of arrays that you have. This is a bit easier when you're talking about Fortran, which is what I'm assuming this question is coming from. In Fortran, yes, it'll support those arrays. In Fortran, you actually don't even need to really shape the arrays oftentimes because Fortran carries that knowledge along with the type. In C, if you have a multiple dimension array, you may need to shape it, though multiple dimension arrays in C are pretty rare, so I'm going to guess this was a Fortran person that asked this question. Also, if you do have multiple dimension arrays in C, you would definitely have to shape it because in C, a multiple dimension array is just a pointer. And so you have to shape it in order to tell it the size of the various dimensions. Continuing to go through and find questions. Just having to get rid of the ones I already answered. Sorry, we have a big document here that's changing quickly. How does the overhead of parallelism compare with OpenMP? That's an interesting question. It's kind of hard to answer without knowing what they directly mean by overhead. But what I can tell you is this, is typically in a well-optimized application, in the time that you launch a kernel, so that's a function that's going to get executed on the device. So when a kernel gets launched, to the point that it launches, it typically takes around 3 to 8 microseconds. And then that kernel runs for some amount of time. So it's a good idea when you do decide where you want your kernels placed, that you put them on larger loops that do a decent amount of work. So if you only have a few, if your loop is only going to go, say, 100 elements wide, it may not be worth putting that one on the GPU. But if your loop is quite big, then it would be definitely worthwhile to put on the GPU. Great. Let me find another question here. Can you explain gangs and vectors? Yeah, I can explain those. There's 4 levels of parallelism, and I'm sure this will be covered more or 3 levels of parallelism. This will be covered more in the future, but we can go over it now. So in OpenACC, you have what are called gangs, workers, and vectors. Now, we can either look at this from the top down, being the coarsest to the finest, or we can look at it from the bottom up, finest to the coarsest. I'm going to go from the bottom up. So at the closest to the SM, right, the finest level of parallelism you have is what's called a vector. A vector can be any size, up to there's practical limits. So any size meaning under say 1024 threads on CUDA hardware. So you can pick your size on that. It's the one that's closest to the device. You can think of a vector almost analogous to say a SIMD type of parallelism. Now, on top of that, we have a collection of vectors, or the group of vectors that you have form a worker, right? So if you have your vector size is 32, then you have one worker of size 32 vectors. Now, I may want multiple workers, so maybe I say I want 4 workers. So then I have 4 workers of size 32 vectors. So a worker is essentially just is your group of vectors. Now, a gang, on the other hand, is a group of workers. So this gives us 3 different levels of parallelism. Typically, if you're familiar with CUDA, a vector and a worker will be assigned to your block. So the product of those will be your block. So you would see like a vector would be your x dimension, your worker would be your y dimension of the block, and then your gang is going to be your number of blocks that you have. Hopefully I answered that question for you. I'm going to go ahead now and find another question. The question is why is the inner loop normally what you want to vectorize? This is a good question. It's not always the case that would be the inner loop is the one that you want to vectorize, but often what we find is a lot of codes will your inner loop is say striding across some field, or reading and writing from some field. So let's say that you're adding 2 vectors together, or you're doing something along that lines, right? You're doing some sort of element-wise operation on the inner loop. In this case, you would often want to parallelize that with a vector because you're going to want that to be your fastest changing dimension in your block. This gives you a better access pattern in terms of memory access. If you're familiar with CUDA, you will know why. If not, I'm not going to go into the details why that is right now, but if you are interested in it, I suggest looking at some of the CUDA optimization talks that we have at GTC to understand what it means when we talk about data coalescing. But in general, yes, you want your innermost loops to be vectorized, and according to the OpenACC spec, you always have to have your order of gang worker vector has to be in that order. So your outer loops have to be a gang, inner loops have to be inside of that has to be a worker, and inside of that has to be a vector. Now you can expose multiple of those on the same loop. So I could have a single loop with a gang, worker, and vector. But what I can't do is I can't, for example, have a worker on the outer loop and a gang on the inner loop. That would be not allowed. You have to have them in order of gang, worker, vector. You're finding another question? So the question is, if I have 12 cores working on a task simultaneously, and each task at some point needs to say, do an FFT on the GPU, do I need to somehow synchronize that traffic? How do I assure that only one CPU thread accesses the GPU at a time? So first off, you can have multiple CPU threads access the GPU at a time, and that isn't a problem. So in this question here, I would have a follow-up question of do you have all 12 threads, all CPU cores, that is, when they get to that point, are they calling a single call into FFT, or are they all where it's one FFT across a shared data structure, or is it a bunch of 12 independent FFTs going forward? So if we'll handle both of those cases in this question. If it's 12 independent FFTs, there should be no synchronization necessary. You shouldn't need to worry about that at all. What you would do is have each of them launch their own work in an FFT. So if you're using QFFT, they'd each get their own handle, and then each launch work into that handle. And so that would be one way you could do this. Now let's say that if you had the 12 threads were operating, they get to a point where they've produced one field that you now want to do an FFT on. At that point, before you call into the FFT library, you better make sure that all of the previous cores have finished computing all the inputs to that. So you would need some sort of synchronization there. And that would be synchronization on the host, something along the lines of if you were using OpenMP, you could either exit out of your parallelism construct, and that would be an implicit barrier, or you could add the pragma OMP barrier at that point. And then when you go launch the FFT, you would launch the FFT from a single core, not from every single one of them. Hopefully I answered that question. If not, please post a follow-up question. All right. I'm just looking for another question here, so I have to kind of read through them a little bit and find good ones. The question is I believe the question is this: is it better to start from OpenACC from scratch, or go do CUDA and come back to OpenACC? And the answer to that is it really sort of depends on what you're doing and what you're comfortable with. So the advantage of OpenACC is that you can do very rapidly accelerate an application, because you can cover a lot of ground a lot of time without a lot of low-level details. Now, when you're doing this, you may not always get the 100% best performance. So what I would typically do is, if OpenACC was something that I was wanting to use, is I would start by using OpenACC. And I would use OpenACC in my application and put as much of the work I can as possible on the GPU. Now, once I've done that, I would go back and I would profile the code. I would find hotspots in the code. A hotspot would be something along the lines of, let's say, this kernel is taking up 50% of my runtime. Now, when I see that kernel is taking up 50% of my runtime, I could get a 2x speed up if I were to take that time down to 0. So what I would do is I would then look at that kernel, try to understand the performance. What is limiting the performance? Can I do things in OpenACC to make it perform better? So for example, can I restructure my loops to expose more parallelism? Can I change my gang workers and vectors to do better? Right? Figure out what the bottleneck is using our performance profiling tools, which we will cover in later weeks. If I run into the point that I cannot get the performance that I wanted to in OpenACC, then at that point, for that one kernel, I would write it in CUDA. And I would write that in CUDA and get the performance that I believe I could, or that I would hopefully I get the performance I believe I could. And then that one kernel is now in CUDA, and the rest of it is in OpenACC. So in this case, I get the best of both worlds. I get the rapid development time that OpenACC provides, and I also get the high performance that CUDA provides. There's no reason for me to go and do CUDA kernels for things that take up a fraction of the runtime. Right? If they take up 1% of the runtime, making that 1% faster isn't really going to help the overall application performance. So I would say using both CUDA and OpenACC is acceptable and encouraged. I also believe that if you're just starting out brand new, jumping into OpenACC is a great starting point. But at some point in the future, you will want to go and understand CUDA at some level, just because it's better to understand what's going on under the hood, as it will help you get better performance in general. Right. So, and that goes on to another question. Somebody was asking, learning OpenACC easier? Yes, I would say OpenACC is a lot easier than CUDA, mainly because it does all the data movement for you. You have to specify data movement, but it's pretty easy. Also, your terms of doing your CUDA kernels, you're just putting some single line saying this loop is parallel, and the compiler is going to do all the hard work for you. So yes, OpenACC is much easier, of course, but with ease of use also comes a potential for the compiler to do something wrong. I'm just going to find another question now. So is it possible to organize concurrent memory copies to the host and kernel? So this is a question on asynchronicity. And the answer to this is yes, you can be asynchronous in OpenACC and in CUDA. So for OpenACC, on your data constructs and on your kernel constructs, there is a clause that you can add called the async clause. The async clause says that this code runs asynchronous with the host. So when that construct exits or enters, that the transfers associated with the data copies or the execution of the kernel is not guaranteed to be complete. You can guarantee completion through a synchronize primitive that's included, but it allows you to be completely asynchronous. I believe we're going to cover this in later weeks. It's a good question, and it's a great way to start thinking about performance. If I have a CPU and a GPU, can I have both of those working at the same time to get the most performance possible? And the answer is yes, you can, and we will cover that later. Question: does the Intel compiler support CUDA? The answer to that is no. The Intel compiler does not support CUDA. It cannot compile CUDA code. If you want to compile CUDA code, you have to use NVCC. That is the only compiler that compiles to CUDA code itself, or compiles CUDA code. Now, if you're referring to, when you say CUDA, it could also mean CUDA hardware. That's a slightly different question, is, does the Intel compiler support CUDA hardware? Again, the answer to that would be no. Intel does not compile down to Nvidia hardware. But, for example, OpenACC compilers do. Intel itself does not support OpenACC currently. Question: is it possible to use a vector clause in a nested loop constructed with a collapse and reduction clauses? I'm not quite understanding the question. I'm going to try to answer it. I'm not quite sure if I've got all of the logic behind this correct in terms of the way things are laid out. But first, let me handle the first part of it. Can you use a vector clause in a nested loop? Yes, you can use it in a nested loop. That would just be the sort of inner loop. That's fine. And if you put a collapse clause on the inner loop to get other inner loops, that would be fine. If you put a collapse clause on the outer loop, then I don't think that would be valid, because that vector clause would have to be on the outer loop, then the same loop that has the collapse. And I am not positive where the reduction comes into this. I don't know if is a reduction on the outer loop or the inner loop. So if it's on the outer loop, that should be fine. If it's on the inner loop, I believe that could also work, but I'm not positive there. Sorry, it's hard without seeing the code example showing you what you want to do if that is supported. The question is, how important is manual gang worker vector splitting to performance? Good question. So is it vital? Is it required? Absolutely not. You do not need to do it. I would consider this a tuning part of your workflow. So you let EGI or Cray or whoever has the OpenACC compiler pick what it thinks is best. And it might do an actual pretty good job at that, and typically it does. It's got some good heuristics where it picks things that it knows are going to be performant across most cases. Now, in your individual case, depending on what your code is doing, you may be able to find slightly better combinations of gang worker and vector to get better performance. Right? At this point, you're taking the control away from the compiler, which is making decisions for you, and saying, I'm going to tell the compiler directly what to do. So you have the potential to get better performance, but you also have the potential to get worse performance. So what you need to do is be careful with that. Make sure you profile or run it afterwards and verify it gets faster, and essentially check your work and make sure that you're getting what you believe. So I would say tuning the gang worker and vector typically might get you an extra 10 to 30% performance. 30% being on the high end that you won't often see. I'm guessing the defaults are pretty good in general, though, like I said, there are cases where you might find better performance by tuning them. Going down, finding another question. Question is, is zero copy in CUDA also supported by OpenACC? It's a good question. So for people not familiar on the phone, zero copy is the ability to pin CPU memory so that it cannot be paged out, and then access it directly on the GPU without actually transferring it in bulk across the PCI Express bus. So that memory resides in CPU memory but can be accessed from the GPU. You should, let me think about this a second. I am going to think that OpenACC probably does, I don't know for sure, but my number one guess here is that it probably does not have a construct to say this is zero copy memory. And I think that if you tried to access that memory from the device, it would give you a compiler error. So I'm going to say that it likely does not support zero copy memory. Though this would be a good question to maybe ask Jeff next week when he presents, because he would have a better idea of that. One thing you can do is simply, if you really want to get a true answer to that question, is to write a quick test case and see if you can get it to work. But I'm going to think that it does not. All right, I'm going to go find another question now. So the question is, you mentioned certain libraries are optimized for use for OpenACC. Is FFTW one? So quick just correction here is that the libraries aren't necessarily optimized for OpenACC. They're optimized to run on Nvidia hardware. And that can be done, they can be written in CUDA, they can be written in OpenACC. Typically our libraries are written in CUDA. Now they can interoperate with OpenACC without a problem. So from the user's standpoint that's writing OpenACC code, there's no difference between using just calling a regular library or calling a CUDA library. The only difference is you might have to pay attention to where memory exists. So that there's a number of libraries that you can use. The question is FFTW one of them? Absolutely it is. We have QFFT is the library that we have for fast Fourier transforms. So yes, you can use that library with OpenACC without a problem. The question here is a good one. I have an AMD R9 GPU without CUDA support. How effective is OpenACC? So to answer this question, first we have to look at what is OpenACC? OpenACC is a cross-platform language that can be compiled down to any hardware, assuming that a compiler exists to compile to that hardware. Currently, the PGI compiler does compile to AMD hardware. So it works just fine compiling down to there and running, and it should run probably with similar sort of efficiencies as you would see on a similar GPU on CUDA. All right, finding another question. Does OpenACC support streams like CUDA does? The answer is yes. We talked about that a little bit earlier. That is the async clause that can be specified on constructs, which says this is now asynchronous. Those essentially map to what we would call streams. If OpenACC is only available for Linux, is it not compatible with DirectX and only for OpenGL? OpenACC is independent of OpenGL and DirectX. DirectX and OpenGL are graphics languages. This is a compute language, so they're independent of each other and unrelated. OpenACC is also available for Windows and Macintosh, not only Linux. Question: does OpenACC make automatic use of multiple GPUs if they're installed? Good question. The answer to this is no, it does not automatically make use of multiple GPUs. There are API calls and constructs in the language itself in OpenACC to specify how to use multiple GPUs. So at that point, you would have to do something like domain decomposition to say put this domain on this GPU and this domain on this GPU and then process on those in parallel. You could think about another way that people often get multiple GPU, and probably the most common way that people get multiple GPU in the sort of HPC space is they will run one MPI rank per GPU, and then have OpenACC or CUDA manage that GPU within the MPI rank. So that's a really good way to get multiple GPU without actually having to go write multi-GPU code, because then all you're doing is writing MPI code. That is probably what you already have if you've been working in the field for a long time. And essentially then you just have, within each MPI process, you are accelerating down to accelerating onto an individual GPU. I'm going to continue to find more questions. Keep them coming. Thank you. Okay, question. What accelerators are supported currently by OpenACC that are not NVIDIA products and now and in the future? So I'm not positive on the exact list of them, but my understanding is PGI can compile down to AMD. I know Xeon Phi and Intel are both on the roadmap to be. I don't know when the timeline is, and they may actually be supported already. But last time I checked into this, it was they were not quite there yet, but they are going to be in the future. In addition, OpenACC could compile down to say FPGAs and such if someone were to write a compiler for that. But currently, I'm not aware of any efforts for that. I'm just finding another question here. What is more efficient, CUDA or OpenACC? And so the answer to that is it depends. In general, right, a well-programmed CUDA code should be at least as efficient as a well-programmed OpenACC code. And the reason is that they could always do the exact same thing. In CUDA, you have a little bit more control, so you can do things that you could not be able to do in OpenACC. Right? You have more control, so you can express things, parallelism designs that you would not be able to do in OpenACC because it's not part of the language. This is what you get from being in a lower level language. However, the effort to do that is going to be significantly more in those cases. So in general, though, a lot of kernels, a lot of them will be on similar level of performance. So they should be essentially equivalent. It's only when you get to some of the more complicated kernels that CUDA might start outperforming OpenACC. Does the compiler optimization levels, i.e. O3, affect OpenACC performance? Well, it will, because that flag will go down into the compiler that's doing the compilation of device code, and then that optimization level will be used when compiling it. So, for example, your kernel, I might have the same kernel with O0 and O3, and in O3, that kernel is going to finish quicker because it was able to use more optimization techniques. We have about a few minutes left still, so I'll continue to do this. Keep asking questions, please. Any questions that we don't answer during this call, we will go ahead and try to answer it within a document afterwards. Finding another question here, so I have to kind of read through these, so please bear with me. Question is, if I have multiple threads executing calculations on the GPU simultaneously, might I exhaust the memory on the GPU by copying in too much data at once? So for example, if the GPU has 1 gig of memory and each CPU core at some point will send down a half a gig of data to the GPU being processed, do I need to manage that memory flow myself? So the answer is yes. If your CPU application has more memory than the GPU is using, than the GPU has, you have to be careful not to allocate too much memory on the GPU at one time. So in this case, if you had the 12 CPU threads, each trying to allocate a half a gig on a device, this would be poor for performance. Right up front, this would cause a sort of out of memory error to be sent, because you would not have 6 gigs of memory on a 1 gig GPU. So you have to be careful with how much you work with that at a time. Unfortunately, there's not a lot of it's not easy to do that sort of allocation. So in those cases, I would suggest the easiest thing to do is to make sure you get a GPU that has significantly more memory. For example, today you can buy the K80 GPU, which has 2 GPUs in it and has 12 gigs each. So generally, the easiest way to work with it is to get larger GPU memories, or larger memory GPUs. So what if I want to parallelize operations on a data set whose memory is much larger than a GPU can support? Can OpenACC handle this? So in this case, what you would have to do is you would have to come up with an algorithm for tiling that algorithm down to memory. So you would have to stream data in and out of the device and process it there. So it would not be as simple as just adding a few pragmas to do this. This would require you to actually modify your code in order to process in tiles as opposed to operate on the entire data set at the same time. It happens occasionally. So for example, you'll see this when you're looking at large matrices. We actually have a library which does this for you for large matrices, and if you're multiplying them together. So that's not an uncommon problem, but it's typically the same sort of stuff you would have to do to be out of core on, say, a GPU or CPU. So for example, if your data set was 4 terabytes in size on disk and you didn't have 4 terabytes of memory, you would have to do some of those same things. Finding more questions? Is OpenACC aware of the specifics of your GPU, or is that what gang worker and vector control is for? The answer is yes, OpenACC is aware. So it's up to the runtime, whoever designs the runtime for the OpenACC, to be aware of this. But they are free to choose gang worker and vectors however they see fit, based on the architecture that you are currently running on. So how hard is it to achieve loop fusion for 4 or more nested loops in OpenACC? So I'm going to kind of look at this question two ways because I'm not quite understanding the questions exactly. So the first one is if you're looping loop fusion, if you mean in terms of looping or fusing multiple levels of the loop together. So if you have an outer loop and multiple inner loops, you can fuse those together pretty easily by using the collapse clause if they're all nested within each other. But there's another type of loop fusion that which you could be looking at, which is if you have, say, a loop, and then that loop exits, and then you have another loop, and that loop exits, and another loop, right? And you want to fuse those all together. So for those, what you would do is you would typically just go and create one loop and then put all the code together in the same loop, as opposed to having three separate loops. And you could do that with multiple nests as you see fit. Someone's asking a follow-up question. This looks like, what's the compatibility in OpenCL? Well, OpenCL has, a bit more compatibility. There are compilers out there for Xeon Phi, and for FPGAs. So it's also more mature than say OpenACC is, which explains why that is. But we expect in the future OpenACC will get a similar level of adoption. Ready? Okay, so here's a good question on OpenACC itself. I noticed one of the examples had a pragma in somebody who's done the examples that we had a pragma OMP parallel inside a pragma ACC kernels block. Does OMP run on the GPU inside the kernels? So the answer here is no, it does not. So when you use OpenMP, right, it's just a hint. Same with OpenACC, it's a hint to the compiler. Now the compiler is free to choose the parallelization scheme that it wants. Now in this case, when you put the pragma ACC kernels in there, what you're seeing is that that's going to turn into some number of kernels. The compiler could, if it wanted to, choose to use OpenMP there instead. So I believe, the way that we really control this is but with the flags that we send to the compiler. So if I don't send the OpenMP compiler flag, then the OpenMP blocks aren't going to be executed. If I don't send the OpenACC flags, then the OpenACC blocks aren't going to be used. It is possible to use both of them at the same time. You can do both OpenMP and OpenACC, but just not in the same loop body. It has to be in different loops that they do it. So I could have the host working on, say, outer loops, and then nest OpenMP inside, or nest OpenACC inside the OpenMP loops. All right, with that, I think we're getting close to running out of time. We just have 2 minutes left, so I believe Julia had a little bit of stuff that she wanted to cover and go over. So I thank everybody for your time. I hope that I answered your questions sufficiently, and we will work on getting your questions answered in a document for you, and any questions that weren't answered, we'll try to get them out to you also. Thank you. And Julia?
Justin, thanks a lot. Really appreciate all your time in answering so many questions. We have quite a few left. We'll try to answer them after the class, and we'll post it in the PDF with the Q&A together with the recording. We'll take a little bit more time to transcribe all the questions, so let's be safe and post it tomorrow, the Q&A, and the recording will be available later today. Then before we go, let me remind you that the next session is the lecture that is scheduled for October 15th. So it will be about 45 minutes of the content and 15 minutes for the questions. But if they have any questions before next Thursday, please do not forget to use Stack Overflow and tag your questions with OpenACC. So we are monitoring this forum as well, so please use that. We highly encourage you. It's a really great tool. And finally, we're always looking for your feedback, so please take a couple of minutes to fill out the survey right after the close the webinar. And one more time, all the recording will be on OpenACC course page. Is developer.nvidia.com/OpenACC-course. So please check it out. Later today we'll post the recording. Thanks again for joining, and see you all next Tuesday. Oh, sorry, next Thursday. It's October 15th. Thanks a lot.